Hello, everyone. Welcome to the Python tutorial session on health trading strategy using machine learning. So in this video, we're going to cover a few different machine learning algorithms and show how they can be used to implement the health trading strategy. Let's get started. I'm using in addition to the web finance, also downloading the torch summary package because it will be useful to help me summarize the model architecture of the neural network later on. Right, so let's get started. As usual, we have the packages to import and then the reproducibility seeds to set. I'm again focusing on the stock price for Google and Microsoft because they seem to be quite co-integrated based on our previous reviews. So this is our stock price again for the full year of 2022 and taking the adjusted closing price. Right, so next we calculate the spread between these two assets in terms of the difference of the log price, right? This is a simple definition of the spread. I'm just using here to demonstrate how you can use it to predict the spread. So this will become our historical data, which we'll be using. And again, our job is to use machine learning models to predict future spread, right? Let's assume that we know the future spread, then we can use that to compare the current rate from the spread and then generate the trading signals. All right, so with the data we have, I'm also going to apply some feature engineering so that we have more features to play around. In this case, I'm using the log price for the stock one. So the difference of the log price, which is the log returns, right, for asset one and for asset two. And another feature is the rolling average of the spread. So this is another feature. Again, this is the technical, commonly used features for technical analysis, right? Again, also the rolling average, the rolling standard deviation for the two assets or the rolling volatility. Right? So these are again a part of a bit of art and science. So you can see which one or what's the best for you, and then try it out and see if it's can help you improve the accuracy of the model. So I'm just going to have 5 attributes, 5 features. So compile them in a data frame so that I can use it to train a model. And then if it's 0, if it's ending, I'm just going to create it 0. And y is the target. In this case, I'm making spread is the target I want to predict. All right. So I'm allocating about 80% of the data to the training set. So this is our training size, and then the rest to the test data set. Right. So the training set will be used to train the model. The test set will be used to assess the performance of the model as a future test set, right? So this is what the data looks like. Let's first train the support vector machine. So I'm just importing the SVR for regression from the package, and then use the mean square error as the error metric to minimize them. So in this case, I'm using a linear kernel. Right, so no linear transformation. After I instantiate by the fit function to train the model, and then the predict function to predict for the given training data set. Right? So in this case, I'm using the prediction for the training set, and then the prediction for the test set, and then measure the root mean square error. So this gives me the root mean square error. Right? So the result shows that the training set error, which is typically smaller than the test set error. Right, so these are the 2 errors, and I can use again. So next, after I build a model, that is the model to implement in the health trading strategy and see how it works. All right, so to facilitate the comparison, I'm just defining a function so that it accepts the model and then returns the final metric, which is in this case, I'm using the terminal return. So I want to say, given a model I have, how is the terminal return look like, right? So I'm having this if-else loop because different models have different ways to make predictions. If it's not a neural network, I can just call the predict function. If it is a neural network, as we mentioned earlier, I'm just calling the model itself, which underlying is calling the fold function, and then passing the inputs or x. Right? And then this is to get the test set performance for the function itself, and detach it, convert it numpy. So this is all more for the neural network model. So after it gets the predicted spread, then we can get the mean and standard deviation for the predicted spread, and then calculate the standardized difference. Right? So this gives us the standardized difference in terms of in the form of the z-scores. So z-scores will be used to generate the training signals. And the only thing different is how we predict the spread. Right? So previously we used the ruling average, the ruling window. But now we're using the machine learning approach to come up with this predicted spreads. So the rest of the code is more or less the same. So you have this threshold for entry and exit, and then the portion for generating the signals. So I'll skip the portion here. And finally, I extract the both returns and together, and then get the terminal return. So this is more or less a standard code. If you need a refresh, please watch the previous videos. Right. So now I have a function and help me to assess the test set performance of a given model. Right? In this case, I'm getting a 1.14 terminal return for the specific model, which is SVM. All right, so let's move on. We assess the random forest regressor next, and I'm having a calculation here. So I have about, so this is 100 trees. So estimator is corresponding to trees. This is 100 trees in the random forest. So the process is more or less the same. Fit the model first, predict for the training set, and then predict for the test set. Gets the root mean square error for training and test set. This is the error metric is seems to be smaller than the essence spotted by the machine, right? But being a more predictive model does not mean that it will produce a better terminal return for the pulse strategy, right? So this is not necessarily guaranteed. So we assess the terminal return, which is 0.91, smaller than the previous model. So this is how we perform comparison. And the next we look at the neural network. So neural network is based on the PyTorch in this case. So I'm just converting all the variables to tensor object, right? To a tensor format. And then we define the neural network architecture. So I have two parts. First one is the initialization. This defines the specifications for the layers. So layer one have this many nodes, so these input nodes based on the features I have in the training data set. In this case, I have 5 features based on the feature engineering earlier. It's 5, and then go to the next layer is 64. And this 64 has to be the same because these 2 layers will need to connect with each other. So this will be the same, 32, 32. Finally, we have 1 output node, right? Output neuron, because our prediction is just the spread itself, right? So it's 1. And we're using ReLU as the activation function. So the fold function basically specifies how the information flows from the input, right, X, flows through the first linear layer, then the activation function, the second layer, activation function, and the third layer. So this is the model architecture, and this is the model weights, right, which we talk about the composition of the model. And then I'm using the summary function from the Torch summary to assess the architecture of the model. We see that we have in total about 2,500 parameters. This is the parameters for each layer, right? There's no parameter for the activation function because it just applies the nonlinear transformation to the weights. So it does not increase or decrease the number of weights, right? So the weights, number of weights is still the same. All right, so next we define the loss function, which is the mean square error, and then the optimizer, which is using Adam. The Adam is sort of the advanced optimizer than stochastic gradient descent and is widely used modern neural networks, right? So with a learning rate of 0.001. All right, so training the network, it's an iterative process. So we train it for 100 epochs. Each epoch, we first zero out the gradients because using gradient descent, we clear the historical gradients first. Apply the neural network to get outputs, right? And then see how's the output doing, how much of difference it has compared with the targets we have. So this is the criteria, which is the mean square error. Then based on the loss, we calculate the gradients automatically. This is using the autograd functionality to do the backward propagation automatically. So this is what backward does. And then perform the gradient descent, right? So change the routes so that it minimizes, it moves towards the direction to minimize the loss. All right, so this is a training loop. And after that, we have the model. So again, the same stuff. We use the model to assess the training and test performance in terms of the root mean square error. All right, so this is our performance metric here. And this is corresponding Sharpe ratio, the terminal return, right? So, all right, so that's not to say that neural network is worse or better than the other models. Again, the process is very complex, right? So even if the model is predictive, the terminal return, which is the metric we're interested in, may not actually be better or worse, right? So this is a two-stage process, and that's to show that how we can possibly use machine learning to change the process in terms of how we come up with the predicted spread. Okay, so that's it for this video, and thanks for watching.